Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today, we're exploring one of physics' most astonishing breakthroughs, the mysterious world of superconductors. Electricity powers nearly every part of modern life, from lighting our homes to driving data across the internet. But as electric current moves through wires, something invisible happens: resistance. No matter how perfect a conductor may seem, a portion of energy is always lost as heat. It's the reason power lines hum, circuits warm up, and devices need cooling. For decades, scientists wondered, could there exist a state where electricity flows forever, without any resistance at all? That question led to the discovery of superconductivity, a phenomenon that seems almost like science fiction. In 1911, Dutch physicist Heike Kamerlingh-Onnes was studying mercury at extremely low temperatures. As he cooled it near absolute zero, something astonishing occurred. Its electrical resistance suddenly vanished. The current could flow endlessly, without losing energy. Onnes had just discovered the world's first superconductor. To understand how this is possible, we need to dive into the strange quantum behavior of matter. In normal metals, electrons collide with atoms as they move, producing resistance. But in a superconductor, something extraordinary happens. Electrons begin to pair up into what physicists call Cooper pairs. These pairs move in perfect harmony, like dancers gliding across a frictionless floor. Because they act as a single quantum entity, they can flow through the lattice of atoms without scattering, without resistance. It's the closest thing physics has to perfect motion. Superconductivity is one of the clearest demonstrations that the macroscopic world we see is ruled by the hidden laws of quantum mechanics. The electron's cooperative behavior is a quantum effect scaled up to human size, allowing entire currents to behave like single particles. But there's another equally fascinating feature of superconductors: the Meissner effect. When a material becomes superconducting, it expels all magnetic fields from within itself. Place a magnet above a superconductor, and it will float, perfectly levitated, held in place by quantum forces. This effect isn't magic. It's the result of the superconductor actively canceling magnetic fields through circulating surface currents, locking the magnet in a stable quantum position. This is what makes superconductors so visually striking. They literally defy gravity. Yet for all their wonder, superconductors have one big limitation: temperature. Most known superconductors only work when cooled to near absolute zero, around -270 degrees Celsius. That means using expensive liquid helium or nitrogen, which limits their practical applications. The quest for so-called room temperature superconductors has become one of the most important frontiers in modern physics. Over the decades, scientists have discovered new materials that push this limit higher. In the 1980s, researchers found a class of ceramic compounds called cuprates that became superconducting at much higher temperatures than metals, above the boiling point of liquid nitrogen. It was a breakthrough so unexpected that it earned the Nobel Prize. But even today, no material has achieved true superconductivity at everyday conditions. Though the race continues, recent discoveries have taken us closer than ever. Using high pressures, researchers have created hydrogen-rich materials that exhibit superconductivity above 0 degrees Celsius. However, the catch is enormous. These materials only remain stable under pressures millions of times greater than Earth's atmosphere, the kind found deep inside planets. The challenge now is to find a way to stabilize these properties without the crushing pressure. If room temperature superconductivity becomes practical, it could transform technology as profoundly as electricity itself once did. Imagine power grids that never waste energy, trains that glide frictionlessly using magnetic levitation, and computers that operate with zero heat loss. Quantum computers, which already rely on superconducting circuits, could become vastly more efficient, enabling leaps in computation power. Superconductors already play a vital role in science and medicine today. Magnetic resonance imaging, or MRI, depends on superconducting magnets to create precise magnetic fields. The Large Hadron Collider uses kilometers of superconducting coils to steer particles at near light speed. These technologies are the first glimpse of what a superconducting world might look like. Yet there's still much we don't understand. The underlying mechanism behind high-temperature superconductors remains one of the biggest unsolved mysteries in condensed matter physics. While the traditional theory, called BCS theory, explains how Cooper pairs form in conventional superconductors, it fails to account for the behavior of these exotic materials. Physicists suspect that electron interactions, magnetism, and even quantum vibrations play roles we've yet to fully uncover. Superconductivity forces us to confront one of physics' most beautiful lessons. The universe's laws often reveal perfection hidden beneath apparent imperfection. What began as an accidental discovery in a frozen laboratory has evolved into a quest for the ultimate conductor, a material that can carry energy without loss, perfectly, forever. Perhaps one day, superconductors will surround us, in our grids, our transportation, even our computing. A future where resistance, both literal and metaphorical, fades away, giving rise to a world where energy flows as effortlessly as thought. This is Mattermosaic, piecing together the universe, one discovery at a time. If you enjoyed this exploration, like the video, share it with others, and subscribe to keep the journey going. Join us in the next episode as we dive even deeper into the strange and beautiful fabric of reality.